Hello everyone, today is day 4 of CodeDrift and today we are going to solve problem named treasure spots. And now let's begin with the reading the problem statement. One day you meet the famous pirate Jack Sparrow and he gives you a puzzle to solve. If you solve the puzzle, all of his treasure will be yours. He gives you n possible treasure spots, each with some value given an array A. He then asks you to count the number of sure treasure spot. A treasure spot with index I will be a sure treasure spot if either a of I modulo a of I plus first is equal to 0 or a of I modulo a of I minus 1 will be equal to 0. It means if either a of I is divisible by a of I plus first or it is divisible by a of I minus 1. He also give you q queries in the form of 2D matrix B. Each query will contain two integer x and y. These are the indices that get swapped after each query. You need to return an integer array containing the number of total treasure spots after each query. So in the end we have to return an array that will contain the answer at the end of the each query. So constraint on this problem is that n is from 1 to 10 to the power 5, where n is the number of treasure spots. Q is the number of the query in any question and Q is from 1 to 10 to the power 5. AI, which is the number stored at the ith index, which is from 1 to 10 to the power 9, and BI0 and BI1, which are the indices which we have to swap in a particular query, that is from 1 to n. Now let's take an example. Now let's take this example of n equal to 7 and e equal to 1, 6, 3, 2, 5, 10 and 15 and q equal to 2 and b equal to 2 and 3 and 4 and 7. So what does this mean is that there are 7 elements in array E and the first element is 1 and the second element is 6 and we have to perform two queries, and in the first query we have to swap element stored at the second and the third index, and in the second query we have to swap element stored at the fourth index and the seventh index. So now let's calculate total number of sure spots for given array A and then we will process the queries. So in order to calculate the total number of nice spot, what we will do is we will iterate over all the indexes and we will verify whether that index is nice or not. So the element stored at the first index is 1 and 1 is not divisible by 6. So 1 modulo 6 is not equal to 0. So this is not a nice spot. And the element stored at the second index is 6 and 6 modulo 1 is equal to 0 as well as 6 modulo 3 is also equal to 0. So this is a nice spot. Element stored at the third index is 3 and 3 modulo 6 is not equal to 0 as well as 3 modulo 2 is also not equal to 0. So this is not a nice spot. And the fourth element is 2. 2 modulo 3 is not equal to 0 as well as 2 modulo 5 is also not equal to 0. So this is also not a nice spot. And the fifth element is 5. 5 modulo 2 is not equal to 0 as well as 5 modulo 10 is also not equal to 0. So this is also not a nice spot. Now for the sixth element 10, 10 is divisible by 5, so this is a nice spot. And for the last element 15, 15 is not divisible by 10, so this is not a nice spot. So in total for the initial array A there are two nice spots, and the first spot is spot number 2 and the last spot is spot number 6. So spot 2 and 6 are the nice spot for the given array A, and now we have to process Q queries. Now to process the first query we will swap the second element and the third element. After swapping them, E will be equals to new A will be equals to 1, 3, 6, 2, 5, 10 and 15. Now let's calculate all the nice index in this new array A. So 1 modulo 3 is not equal to 0, so this is not a nice index, and 3 modulo 1 is equal to 0, so this is a nice index. And for the 6 modulo 3 is equal to 0 as well as 6 modulo 2 is also equal to 0, so this is also a nice index. For the fourth index, element stored is 2 and 2 modulo 6 is not equal to 0 and 2 modulo 5 is also not equal to 0, so this is not a nice index. And for the fifth element 5 modulo 2 is not equal to 0 and 5 modulo 10 is also not equal to 0, so this is not a nice index. For the second last index the element is 10 and 10 modulo 5 is double equal to 0, so this is a nice index. And for the last element 15 modulo 10 is not equal to 0, so this is not a nice index. So after processing the first query there will be three nice index number 2, 3 and 6. So in the first query we swap the second element and the third element, and as we can observe only the value for the index first, second, third and the fourth got updated and all the remaining value remains the same. So only these four values got updated. And now let's process the second query. To perform the second query, we will swap the element which are present at the index number 4 and index number 7. So after performing the query, A will be is equals to 1, 3, 6, 15, 5, 10 and 2. Now let's calculate total number of nice index in this new array A. So the first index is not nice index as 1 modulo 3 is not equal to 0. Second index is a nice index as 3 modulo 1 is equal to 0. So this is a nice index. The third index is also nice index as 6 modulo 3 is also equal to 0. So this is also a nice index. The fourth index is a nice index as 15 modulo 5 is equal to 0. So this is a nice index. The fifth index is not a nice index as 5 modulo 15 is not equal to 0, as well as 5 modulo 10 is also not equal to 0. So this is not a nice index. Element stored at the index number 6 is 10 and 10 modulo 5 is double equal to 0. So this is a nice index. Last element is 2 and 2 modulo 10 is not equal to 0. So this is not a nice index. So at the end of the second query, there will be 4 nice index 2, 3, 4 and 6. So here we can observe that we swap the 7th element and the 4th element. So we swap these element and only the value for this index, this index, this index, this index and this index got updated. Now let's take a generic case when we are swapping the element present at the index x and at the index y, then only the status of the index x minus 1, x plus first, y minus 1, y and y plus 1 will get changed. So what we can do is we can find all these index and subtract how much they were contributing to our final result. After that we swap these element present at these two indexes, then recompute the result for these 6 indexes, then add that result back to our final result. So in this way we can find the total number of nice indexes after each query in just constant time. Now let's go through the solution code. So we have created a helper function check. It takes array A and index as its argument and it will verify whether A of index is divisible by A of index minus 1 or A of index plus first. If either of that case is possible, it will return 1. In all the other cases, it will return 0. Now moving on to our main solution, in the function solve we are getting array A and 2D matrix B as our argument. After that we are computing the length of array A and we are initializing our answer to 0. So in this statement here what we are doing is that we are iterating over all the index and calculating our answer before processing any query. So here what we are doing is we are creating an out array. This array will store our final result that we have to return at the end. And after that what we are doing here is we are iterating over all the queries. So what we will do is we will process each query one by one, and after that we will append it answer to our out array, and then in the end we will return the out array. So here we are subtracting 1 from x and y as our array is 0 base index here. So what we are doing is we are shifting everything to the left by 1. Then we are creating an array ls. So this array ls will store index of all the element that we have to update in this query. And after that what we are doing is if x is greater than y, then we are swapping x and y. So after this statement x will always be less than y. If x is greater than y, then we are swapping x and y here in this statement. After that x double equal to y. So this case will be true when we want to swap two elements which are present at the same index. Here are two elements. The first element is at this location and the second element is also at this location. So we are swapping an element by itself. So we are actually not doing anything. So we will append the previous answer to our out array and we will continue to the next query. And if x plus 1 is equal to y or x plus 2 is equal to y. So this case will be true when this is x and y is just after x, or this is x and there is some other element and after that there is y. Both these cases are special and here we are considering them separately, and we are appending all the elements which are adjacent to either x or y to our array ls. And in all the other cases we are iterating over -1, 0 and 1, and after that in this statement here we are appending x minus 1, x and x plus 1 to our array ls, and in this statement here we are appending y minus 1, y and y plus 1 to our array ls. Here we are iterating over all the elements of ls and subtracting how much that index was contributing to our answer. And after that we are swapping the elements present at the index x and at the index y, and after that we are again computing how much each index of ls is contributing to our answer and we will add it. So what we did is we calculated an updation array ls for each query, and after that we subtracted how much that each element was contributing to our final result, and after swapping we again added how much each element will contribute now to our final result. After that we appended answer to outs, which is storing the answer of each query, and in the final statement, after iterating over all the queries, here we are returning our final result. Now let's analyze the time complexity and space complexity of our solution. So the time complexity of our solution will be O of n plus q, where n is the size of array A and q is the number of query. So this time complexity comes from the fact that before performing any query, what we are doing is we are iterating over all the elements of array A, and we are calculating how much this index is contributing to our final result. After that step, we are iterating over all the queries, and for each query we are computing what index we have to update, and for each index we are calculating the check function twice. So all the computations that are inside this for loop will take constant time, and there are q queries, so the time complexity of our solution will be O of n plus q. Space complexity of our solution will be O of q, because we are creating array outs to store our final result that we have to return in the end. Now we are going to solve the second problem of today, that is another tree counting problem. In this problem you are given a tree that has n nodes and n minus 1 edges. A matching of a tree is defined as a subset of edges of this tree such that no two edges share a common vertex. A number of this matching is defined as assigning a value to each node that is present in this matching. If there are e edges present in this matching, then there will be 2e nodes in this matching. Now what we will do is we will assign value to each node in this matching. For each node with index I in the original tree, its value should be an integer from 1 to a of I inclusive. So for each edge that is present in this matching, its weight will be value of u and with value of v, where u comma v are the endpoints of the edge and AND is a bitwise AND operation. The total cost of numbering of a matching is defined as the sum of weight of all the edges present in this numbering of the matching. Your task is to calculate sum of cost over all the numbering of all the matching, modulo 10 to the power 9 plus 7. Constraint on this problem is that n is from 1 to 10 to the power 5, where n is the total number of nodes in the tree, and a of 1, a of 2, which are the maximum value that can be assigned to a node, is from 1 to 10 to the power 9. Now let us take an example to understand this problem. Now let's take this example of n equal to 7, a equal to 4, 11, 2, 3, 2, 7, 1, and b equal to 1, 2, 1, 4, 3, 4, 7, 5, 6, 5, 5, 1. So what does this mean is that there are 7 nodes in our tree, and the maximum value that node 1 can take is 4, the maximum value that node 2 can take is 11, the maximum value the node 3 can take is 2, and so on. So this will be the corresponding tree. Here we have arbitrarily routed the tree to 1. So this will be our root, then 1 is connected to 2. So from this edge 1 is connected to 2, 1 is connected to 4, 4 is connected to 3, 5 is connected to 6, and 5 is also connected to 1, and 7 is connected to 5. So this will be our corresponding tree. Now let's replace the each node value with the value of that node in the array A. So value of the node 1 was 4, so we have replaced 4 here, and the value of node 2 was 11, so we have replaced 11 here, and the value of node 3 was 2, so we have replaced 2 here, and the value of node 4 was 3, so we have the replaced value 3 here, and we will get this new tree. So we will get this new tree where each value will represent what is the maximum value it can take in the final matching. There are many valid matching and many valid assignments to each node. Now let's take one example of that. So now let's take that we have considered this edge, and this edge in our final matching, and we have assigned the value of 1 to this node, and value of 2 to this node, and the value of 3 to this node, and the value of 11 to this node, and 1 to this node, and 5 to this node. So our final answer will be is equals to 1 and with 2 plus 3 and with 11 plus 1 and with 5, and it will be is equals to 0 plus 3 plus 1, and it will be is equals to 4. So for this matching our final answer will be 4, and now we have to iterate over all the assignment and all the matching and calculate our final answer, which will be is equals to the sum of all those matchings. Now if we try to solve this problem by taking all the assignments to each node and all the matching that we can do, then this solution will be very slow. Now let's try to optimize this solution. So what we can do is we can think of a bottom-up dynamic programming, in which what we do is we will first solve the same problem for every child, and after that we will compute how can we solve this problem of this parent in the terms of all the child. So for that we have to create two arrays ways and sums. So what does way array denote is that way of I comma 0 is denote that the ways of numbering and matching of the subtree I such that ith node is not connected to its child. And way of I comma 1 denotes that number of ways of numbering and matching of the subtree of I such that the ith node is connected to one of its child. Now ways of I comma 0 can be calculated as we will iterate over all the childs of I, and after that we will take the sum of ways of j0 and ways of j1, and then we will take product of all these child. So this formula comes from the fact that if there is one node here and it has multiple childs, then and we have decided that we are not going to connect this node with any of its child, and if this child can solve the problem of its subtree in a ways, and this child can solve the problem of its subtree in b ways, and this child can solve the problem of its subtree in c ways, then the total number of ways will be a multiplied by b multiplied by c. And it doesn't matter whether this child is connected to its own child or not, or this child is connected to its own child or not. That's why we are taking the sum of ways of j0 plus way of j1. And ways of I1 can be calculated as summation over all the child ways of j0 multiplied by a of j multiplied by ways of I0 and divided by way of j0 plus way of j1. So this formula comes from the fact that if there is some parent and it has multiple children, for this example it has like 4 children, and we have decided that we want to connect this parent with one of its children. So what we will do is, first we are going to fix a children, then this node can take a of I values, this node can take a of j values, so this term are coming from that. And after that we want to solve this problem for its subchildren, but for that we want that this node is not connected with any of its children, so this terms comes from that. And for the all the other node like this node and this node, these node may or may not be connected with their own children. So for that this term and this term comes from that fact. So here what we are doing is we are multiplying the ways of all the children combined, and after that dividing by the ways of this specific node. So it will be is equals to the product of all the other node except this one node. So this is like a prefix multiplication of these node and suffix multiplication of all these node. Now we will iterate over all the child, and we will assume that now we are connecting this parent with this specific child, and we will add all the results. Now let us see what is sum array and how to compute it. Now let's understand what this sum array is. So sum of cost over all the numberings and matching of the subtree I. So sum of I of 0 denotes that the sum of cost over all the numberings and matching of subtree of I such that the ith node is not connected to any of its child. Sum of I1 denotes that the sum of cost over all the numbering and matching of subtree of I such that the ith node is connected to some child. So sum of I0 and sum of I1 means that we have solved the problem for the ith node and whether that ith node is connected to any of its children or not in that specific solution. So if we arbitrarily route our tree to some node m, then in the end our final answer will be sum of m0 plus sum of m1. So this would be our final answer. Now let's understand how to compute these sum arrays. So now in order to calculate sum of I0, what we will do is we will iterate over children, and let's say we have considered this children and this is the parent, and we have decided that we are not going to connect this node with any of its children. And now we want to calculate how much the sum of this specific one node is going to contribute to the subtree of this parent node. So for that what we will do is we will take the entire sum of this specific node and multiply by it with the total number of the ways of the prefix multiply by with the total number of ways of the suffix. And this is the formula to calculate that, and this formula comes from the fact that what we will do is first we are going to fix this specific node, and if the first child can solve the problem recursively for its children in A ways, the second child can solve the problem for its children in B ways, and all these other nodes can solve the problem for their child in F, G and H ways, then the total answer will be A multiplied by B multiplied by F multiplied by G multiplied by H multiplied by the total sum this node was contributing. So that is this formula. Here what we will do is we will multiply it by the prefix, we will multiply it by the suffix, and we will calculate the sum of that specific node. So this is how much a specific node is going to contribute to its parents overall sum, and we will take the sum over all the children. Now let's try to understand how we are going to compute this prefix multiplied by the suffix term. So this term is nothing but equal to the multiplication of all the term except for the jth term. So it will be equivalent to total number of ways divided by the ways of the jth node. So the total number of ways such that the ith node is not connected to its children is given by ways of I0, and total number of jth node is given by ways of J0 plus ways of J1. And this is how we are going to compute this term in our solution code. First we will divide by this, and in the end we will multiply by this term. So in way of I1, we are already assuming that we have connected this ith node with one of its children. And after connecting a node with its children, there are three major components in order to compute sum of I1. One is the edge component, edge child component, and non-edge child component. So now first understand how we are going to calculate the edge component. Now in order to calculate the edge component, we will iterate over all the nodes j such that j is some child of node I, and after that we are taking ways of j0 multiplied by the prefix multiplied by suffix, and then how much that specific edge is going to contribute. So if we are connecting this edge between this parent and this child, then we want that this node must not be connected with any of its children. So that's why we are taking way of j0 here, and after that we are going to take prefix multiplied by the suffix. So this comes from the fact that in how many ways these node other than this specific node are going to solve the problem for its sub children. And after that we are calculating the edge contribution, how much that specific edge is going to contribute to our answer. Now let us take an example to understand how we can calculate edge contribution. So we have taken an example of ai equal to 3 and a of j equal to 5. So this means that this node can take any value from 1, 2 and 3, and this node can take any value from 1, 2, 3, 4 and 5. So now if the ith node is taking the value x and the jth node is taking the value y, then our final contribution will be x and with y. So here we are ending the two values. So now we will consider a bit by bit, and we will consider how much each bit will contribute to our final result. Now let us take an example of the 0th bit. Now after ending the two numbers, how many times the 0th bit will be turned on even after the ending. So that can be given by in how many ways the 0th bit will be on here, and in how many ways the 0th bit was on here. And after that we will multiply these two numbers. So it was turned on for the 2 times in the first number, and it was turned on for the 3 times in the second number. We will multiply them, and we will multiply them with 2 to the power 0. So this is how much the 0th bit will contribute when we will take the value of x from these three numbers and value of y from these three numbers. And the same goes for the first bit and the second bit. And value of ai is constrained by 10 to the power 9. So in order to calculate the edge contribution, we will iterate over first 30 bits. And this is how, in order to calculate edge contribution, we have to take the contribution of each individual bit first, and after that we will add them up to get the entire edge contribution. Now let us calculate the edge child component of sum of I. So now what we are doing is we are taking the sum of j0 multiplied by ai multiplied by aj multiplied by the prefix and multiplied by the suffix, and taking the summation of these product over all the childs j. So this formula comes from the fact that if there is some node I and it has, let's say, 4 children, and now we have decided that we are going to connect this parent with this child, then there are a of I multiplied by a of j ways to connect this one edge, and prefix ways to solve this problem for the subchild of the prefix, and suffix ways of solving the problem for the subchild of this suffix. And sum of j0 is the total sum that this node will give, such that it has been not connected with any of the other node in its children, and hence we will get this entire formula. So this is the sum, and this is the number of ways this sum will be repeated. So now we have to calculate the non-edge child component. So now let us take an example that how many times this component will be repeated. So to do that, we will always consider that we are connecting this parent with all the other node other than this jth node. So what we will consider that, first we will consider that we are connecting the ith node with this node, then ith node with this node, then ith node with this node, and then ith node with this node, and this ith node with this node. And each time we will calculate how many times this sum of j0 plus sum of j1 will be repeated. Now let us take an example that we have connected this ith parent with this k, which is the child of this ith node, and then there are a of I multiplied by a of k ways to make this edge connection, and multiplied by way of k0, because we don't want this node to be connected with any of its children. And after that, for all the other node other than jth node and the kth node, like this node, this node, this node, and this node, we will multiply in how many ways these each node can solve the problem for their subchildren, and we will multiply them. So this is the sum, and this is the total number of time that sum will be repeated. So we will iterate over all the j nodes such that j is some children of I, and after that we will iterate over all the children of I such that they are not equal to j, and we will take their sum. So this was non-trivial problem on tree, and we have solved this problem in bottom-up fashion. So to compute the results of any node, we have to first solve the problem for each of its child. So now we will use DFS to solve this problem. We will first of all route the tree to any arbitrary node, then we will start our DFS, and after that we will reach each node, and then we will solve the problem for each of its children, and then we will compute the results for that node, and then we will move back to its parent. Now let us look at the solution code. We have created a helper function count. It will take two arguments n and I, and it will return in how many numbers from 1 to n they have the ith bit set to 1. So first of all it will shift n by I bits, then it will initialize answer to 0, and then it will check if the 0th bit in p is set to 1 or not. If the 0th bit was set to 1 in our p variable, then it will add the n minus p into 1 shifted by I plus 1 in our answer. Then it will subtract 1 from p, and then it will add the 1 shifted by I bits and multiplied by p plus 1 shifted by 1 bits to our answer, and then it will return it. Second helper function is cost. It takes two value u comma v. So this helper function is used when we have to calculate the contribution of each edge. So it will take the two values that an endpoint of an edge can take, and after that it will take the contribution of each individual bit, add them all up, and return the result. Here we are iterating from 0 to 29 and calculating the contribution of each individual bit, and then it is calculating in how many numbers from 0 to u and 0 to v they have the ith bit set. Then it is multiplying the result by 2 to the power I and adding it to our final result answer, and in the end it is returning the answer. So in the solution code we are getting variable a and variable b respectively, where a is the maximum value a node can take and b is the list of all the edges. We have created two global variable g and a to store our tree and value of array a globally, and after that we are computing the length of array a in variable n. After that we are copying local a to global a. Then we are iterating over all the nodes and we are clearing the graph, and after that we are iterating over all the edges and appending those edges in our tree so we can traverse them. After that we are starting the DFS from 0, -1. When the DFS will be over, our final result will be stored in answer of 0, 0 and answer of 0, 1. So here we are returning our answer. So in our function DFS we are getting I comma parent, where I is the node and parent is the parent of that node. After that we are initializing way of I0 to 1 and way of I1 and answer of I0 and answer of I1. So this answer is equivalent to sum in our explanation, and we are initializing all these values to 0. And after that we are creating four variable sm, sm1, sm2 and sm3. So these four variable will be helpful when we will be creating edge contribution, a contribution of edge child node and a non-edge child node. For that these four variable will be useful. After that we are iterating over all the childs of node I, and if j is not equal to parent, we are first starting a DFS over that child. Then we will multiply way of I0 with way of J0 plus way of J1. So here we are computing way of I0. Here we are computing modulo multiplicative inverse of ways of J0 plus ways of J1. So this modulo multiplicative inverse will be useful when we want to calculate prefix multiplied by suffix. So what we will do is we will take the entire multiplication and then we will divide it by ways of J0 plus ways of J1. So this will be equivalent to prefix multiplied by the suffix. After that we will add a of j multiplied by a of j0 multiplied by the inverse to our ways of I1, and here we are adding answer of j0 plus answer of j1 multiplied by inv modulo mod to our answer I of 0. So here we are computing way of I1 and here we are computing answer of I0. So this sm variable is used to calculate the contribution of each edge. So this is equivalent to how much each edge will be contributing multiplying by the total number of ways. And this sm1 and sm2 variables are used to calculate the contribution of each non-edge child. So we will add a of j multiplied by way of j0 multiplied by inverse into sm1, and we will add answer of j0 plus answer of j1 multiplied by a of j multiplied by way of j0 multiplied by inverse and multiplied by inverse into sm2, and this sm3 is used to calculate the contribution of each edge child. So now we will add answer of j0 multiplied by a of j multiplied by inverse into sm3. So these two terms ways of I0 and a of I were common in the formula of ways of I1. So we have taken these two terms out common, and now we will multiply these two terms to ways of I1, and now we will get the final result of ways of I1. Formula for answer of I1 will be is equals to ways of I0 multiplied by Sm plus E of I multiplied by ways of I0 multiplied by Sm multiplied by answer of I0 minus Sm2 plus Sm3, and answer of I0 will be is equals to ways of I0 multiplied by answer of I0 modulo mod. So these formula are just the simplification of the formulas that we have discussed in our explanation. Now let's analyze the time complexity and the space complexity of our solution. So the time complexity of our solution is O of n log mod, where n is the total number of nodes in the tree and mod is 10 to the power 9 plus 7. So this time complexity comes from the fact that we are visiting each node exactly once, and whenever we are visiting a child from its parent, we are computing modulo multiplicative inverse of ways of 0 plus ways of 1. So the time complexity will be n of log mod. So the space complexity of our solution will be O of n, because we are creating two arrays answer and ways, and they will take O of n space. Thank you for watching. Please like and subscribe and stay tuned.